everyone, and welcome to the Environmental Science and Engineering Podcast channel. In this episode, we will be talking about the design of wastewater treatment plants. This topic covers a very broad area, so we will divide it into several episodes. In the first episode, which is today's, we will discuss fundamental topics such as what wastewater is, the content of domestic and industrial wastewater, how pollutant parameters are defined, how population and flow rate calculations are performed, and where the plant should be located. In later episodes, we will move on to process design, sludge treatment, and more technical details. We believe this will be very useful for environmental engineering students, academics, and professionals working in the sector. First, I would like to welcome our expert guest.
Thank you. I'm happy to be here. This is indeed a very important topic, and it will be very beneficial to cover all aspects of wastewater treatment plants step by step in this series.
I'd like to slowly dive into the topic, and I want to start with a question. What is wastewater? What types of wastewater are there?
That's a great question to start with. Thank you. Wastewater can actually be divided into two main groups: domestic and industrial wastewater. Domestic wastewater is the waste produced by people in their daily lives. All the water generated when we wash our hands, flush the toilet, or run washing machines or dishwashers falls into the domestic wastewater category. On the other hand, industrial wastewater originates from production processes in industries. This group includes water discharged from a factory's process or water generated in a food processing facility. Other examples, such as wastewater from slaughterhouses or car wash areas, are also included in the wastewater classification. There is also stormwater. Normally, stormwater should be collected in a separate line, but in some cities, the storm sewer and sanitary sewer lines operate as a combined system. In such a case, the pollution flowing from streets and highways along with the rain can also be carried to the wastewater treatment plants. This creates an additional load on the facilities.
Now, I'd like us to talk a little bit about the structure of the city where the wastewater treatment plant will be built. Because people generally think we'll build the plant, we'll treat the water, but the job is actually not that simple. The city's population structure, growth rate, and even seasonal variations directly impact the design, don't they?
Absolutely. The first thing that needs to be looked at when designing a wastewater treatment plant is the city's population and population growth trend, because the plant's capacity is directly determined by this population. If you can't accurately calculate the daily amount of wastewater generated, the plant will either be unnecessarily oversized, leading to a waste of resources, or it will become inadequate in a short period.
So when designing a wastewater treatment plant, calculations must be made not based on today's population, but on the future population. How are these predictions made?
There are several different population forecasting methods for this. The most classic ones are the arithmetic increase, geometric increase, logarithmic increase, and decreasing rate of increase methods. For example, the population data of the last 20-30 years in a city is collected, and then a projection for the future is made with this data. This allows us to predict what capacity the plant will need in which year. Wastewater treatment plants are generally planned for periods of 30 to 50 years. However, this period is not covered in a single phase. For example, a 30-year plant is constructed in 2 or 3 stages. For instance, in a 30-year plant, the first stage is built for the initial 15 years, and then the second stage is commissioned as the population grows.
So let's say we are currently building a plant for a city of 100,000 people, but if the population is expected to rise to 150,000 in 15 years, then we need to increase the capacity by 50%.
Exactly. And if the population is expected to reach 200,000 at the end of 30 years, the capacity should be doubled. These expansions are usually achieved by adding new reactors and tanks in previously planned empty areas. This way, the plant can expand without disrupting the existing infrastructure.
Well, when determining the capacity of a water treatment plant, not only the population but also the per capita water consumption must be an important factor. I guess this value changes from country to country and even city to city?
Yes, that's absolutely right. The amount of wastewater produced by one person each day generally ranges from about 100 to 300 liters. However, this depends on how developed the country is. In less developed countries, people typically generate around 50 to 100 liters of wastewater a day. That's because access to running water is limited, saving water is a necessity, and sewer systems are often inadequate or even non-existent. Since people use less water, naturally, less wastewater is produced. In developed countries, this amount is much higher, usually between 150 and 400 liters a day. For instance, in the United States, it's roughly 400 liters per person daily, around 200 liters in Europe, and about 190 to 200 liters in Turkey. The main reasons for this difference are the constant and pressurized water supply, higher living standards, greater industrial and commercial activity, and complete sewer infrastructure. In other words, almost all the water used eventually becomes wastewater.
So, how are calculations made in places where industries are also present, meaning where domestic and industrial wastewater are collected together?
Yes, equivalent population is quite a critical concept. Basically, it allows the pollution load exerted by an industrial facility on the environment to be made equivalent to that of one person producing domestic wastewater. For instance, a person typically generates a BOD load of approximately 60 grams per day. If a factory produces 600 kilograms of BOD per day, the equivalent population of this factory is considered to be 10,000 people. This way, domestic and industrial wastewaters can be evaluated on a common scale, and the total capacity of the plant is planned accordingly. Thus, the plant's design is optimized not just according to the number of people, but also according to the pollution load. This is crucial because a residential area with 5,000 people might produce as much wastewater as a highly polluting industrial zone.
You also mentioned that stormwater can mix into the sewer system. Is there a difference between older and newer infrastructure?
Yes, this is the flow rate we call infiltration rate. The infiltration rate is the amount of water that unintentionally enters the sewer system. This usually occurs when groundwater, stormwater, or drainage water seeps into the system through cracks in the pipes, joints, or manhole covers. This rate can be very high, especially in older infrastructure. In some cities, the infiltration rate can even reach up to half of the actual wastewater flow. This increases the hydraulic load, causing pumps to consume more energy, aeration basins to overflow, and treatment efficiency to decrease. That's why engineers usually account for the infiltration rate in their projects with a specific allowance. For example, they might add it to the design at a rate of 50 to 100% of the dry weather flow, or based on 0.1 to 0.2 liters per second per hectare.
So ultimately, per capita water use, equivalent population, and infiltration/inflow rate, these three together are the cornerstones for accurately determining the capacity of a treatment plant.
Absolutely. A design made without considering these three parameters will become unsustainable in the long run, both technically and economically.
So far, we have talked about capacity and population calculations for a water treatment plant. But before all of this, there is another very critical decision to make: where the plant will be built. Site selection can often be much more complex than the technical design itself. What are the most important factors in selecting a site for a wastewater treatment plant?
I can say that site selection determines the fate of a treatment plant, because poor site selection can both harm the environment and reduce the plant's operational efficiency. The first thing to consider is the distance from residential areas. The plant should be located away from city centers, with a dominant wind direction and analysis being critical. If the wind direction is not considered, odors can be carried directly to residential areas. For this reason, a green protective belt and a forested buffer zone is usually left in between. Secondly, the topography, slope of the land. The slope determines whether the plant can operate by gravity. If the slope is suitable, wastewater flows naturally to the plant without the use of pumps, which reduces energy costs. However, a very steep area poses a risk of landslides, and a very flat area leads to significant excavation and filling costs. Therefore, the plant should ideally be built at the lowest elevation of the settlement area, at a point where wastewater can flow by gravity. Also, there should be a minimal slope within the facility itself. The water must flow by gravity within the plant. You wouldn't want the water level of the primary sedimentation tank to be 100 meters and the final sedimentation tank to be 110 meters. The elevations. It is preferred that the elevation of the plant's inlet is always higher than the outlet. The plant should not exceed a 5% slope within its borders. Thirdly, the discharge location. The plant must be close to the receiving body so that the discharge line is short and economical. However, this area must not be at risk of flooding. In other words, a plant should not be built in areas prone to inundation during rainy seasons. This ensures both environmental safety and operational continuity. Fourthly, criteria related to civil engineering are also important. The foundation soil must be stable and free from the risk of settlement or liquefaction. Furthermore, if the groundwater level is high, there will be infiltration problems during construction, which is both economically and structurally risky. Fifth, the plant should be close to main roads and power lines. Easy access reduces operational costs and provides a significant advantage when emergency intervention is required. Electricity supply should also be sourced from the shortest possible distance. Sixth, expandability. Plants are usually designed with a 30 to 50-year projection. In the first phase, it might serve 100,000 people, but a second or third stage is added over time. Therefore, areas with expansion potential should be preferred. This means leaving empty spaces around the plant where a new reactor or sludge dewatering unit can be added in the future. Finally, social acceptance. The sensitivity of the surrounding public, the existence of agricultural lands, drinking water protection areas, and conservation zones must be considered during site selection. It is not appropriate for the plant to be close to drinking water basins, irrigation areas, or national parks. In addition, environmental impacts, odor, flies, noise, gas emissions must be analyzed with meteorological data.
So, proper site selection actually means striking a balance right in the middle of environmental protection, technical efficiency, and social acceptance.
Exactly. The foundation of a successful treatment plant project is building it in the right location. Poor site selection can render even the best technology ineffective. The decision on site selection must be made by evaluating technical, economic, social, and environmental factors through both qualitative and quantitative analyses.
Let's talk a little about the basic parameters measured in wastewater treatment plants, because the success of the plant is actually measured by how much these parameters can be reduced. Which parameters are among the most critical?
The most important parameters in wastewater treatment plants are chemical oxygen demand, COD, biochemical oxygen demand, BOD, total nitrogen, TN, total phosphorus, TP, and total suspended solids, TSS. These parameters represent the amount of organic matter, nutrient elements, and solid particle load in the water. The primary goal of treatment plants is to remove organic pollutants, nitrogen, phosphorus, and suspended solids present in the water. Accurately measuring these parameters is the most direct way to evaluate the plant's performance.
So, the pollution load in the water is represented by these 5 basic parameters. What is the typical range for these values for a typical domestic wastewater?
In classic domestic wastewater, the COD is approximately at the level of 500 milligrams per liter. The BOD is around an average of 300 milligrams per liter. The TSS typically ranges between 250 and 300 milligrams per liter. The TN concentration is approximately 40 milligrams per liter, and the TP amount is usually around 10 milligrams per liter. These values are valid for purely domestic wastewater. However, if industrial wastewater mixes into this system, the concentrations both increase and become quite unstable.
The pH value of domestic wastewater is typically in the range of 6.5 to 8.5. This range provides the most suitable environment for biological treatment because the microorganisms responsible for the treatment process work most efficiently within this pH range. In more acidic or more basic environments, the activity of microorganisms decreases and consequently the treatment performance also drops.
Okay, what are the target values that these parameters must be reduced to after treatment? In other words, how strict are the discharge standards?
Discharge standards vary by country, but very strict values are applied in developed countries. COD should generally be below 125 milligrams per liter. BOD should be less than 30 milligrams per liter. TSS must be reduced below 35 milligrams per liter. TN is usually kept around 10 milligrams per liter, and TP is often reduced to below 1 milligram per liter. The purpose of these limits is to protect the ecological balance of the receiving environment, the lake, river, or sea, where the treated water is discharged. Especially, an excess of nitrogen and phosphorus leads to a process called eutrophication in aquatic environments. This causes an overgrowth of algae, a decrease in dissolved oxygen, and a threat to the life of aquatic organisms.
Let's talk a little about the processes used in treatment plants, because the same method is not applied in every city. The system used varies depending on both the population and the land structure. What is the most common process used?
The most common method used in wastewater treatment is the activated sludge process. This system has become the standard for treating domestic wastewater in cities. In activated sludge systems, organic substances in the water are broken down by microorganisms in the presence of oxygen. These microorganisms reduce the organic load in the water and are then separated from the water in settling tanks. During this process, a part of the sludge is returned to the system and the remainder is removed from the system. Correctly adjusting the oxygen supply, sludge return rate, and retention time in the basins is critical for the system's efficient operation.
So, microorganisms are essentially the main actors in the treatment process. Do these microorganisms work the same way in every system?
No, microorganisms can actually grow in two different ways: suspended growth systems and attached growth systems. This distinction depends on where the microorganisms live and proliferate. In suspended growth systems, microorganisms float freely in the water. That is, they remain suspended in the water without clinging to any surface. Continuous aeration and mixing are required in these systems to keep the microorganisms alive. The most common example is the activated sludge system. Sequential batch reactors, or SBRs, and membrane bioreactors, or MBRs, also fall into this category. The advantage of suspended growth systems is the high treatment efficiency and the flexible control of operating conditions. However, energy consumption is high due to the need for continuous aeration and a large amount of sludge is produced. In attached growth systems, microorganisms grow as a film layer by attaching to a surface. This surface can be rock, plastic material, or special carrier elements. This layer formed by the microorganisms is called a biofilm. As the wastewater passes over the surface of this biofilm, the organic substances within it are broken down by the microorganisms. These systems usually have both aerobic and anaerobic zones. This allows for the removal of not only organic matter, but also nitrogen and phosphorus. The best-known examples are trickling filters, rotating biological contactors, and moving bed biofilm reactors. The most important advantages of these systems are their robustness, low energy consumption, and low sludge production. However, if the biofilm layer thickens, the inner part can become anaerobic, and in this case, the treatment efficiency decreases.
So, microorganisms sometimes live freely in the water and sometimes attached to a surface. This difference completely changes the type of system. Are there any more specialized or advanced systems besides these?
Yes, there are. Constructed wetland systems are generally preferred in rural areas. These systems mimic the treatment mechanism of natural wetlands. Plants, microorganisms, and soil work together to purify the water. Energy demand is low, operating cost is minimal, and they are compatible with the nature.
However, these systems can't be implemented in high-flow cities due to insufficient land area. In large cities, advanced biological treatment systems are used. These systems are more developed than classic activated sludge processes and also remove nutrients like nitrogen and phosphorus. For this,
Yes, there are. Constructed wetland systems are generally preferred in rural areas. These systems mimic the treatment mechanism of natural wetlands. Plants, microorganisms, and soil work together to purify the water. Energy demand is low, operating cost is minimal, and they are compatible with nature. However, these systems cannot be implemented in high-flow cities due to insufficient land area. In large cities, advanced biological treatment systems are used. These systems are more developed than classic activated sludge processes and also remove nutrients like nitrogen and phosphorus. For this, sequential processes such as nitrification, denitrification, and biological phosphorus removal are operated together. The effluent quality in such systems is high and is generally suitable for reuse. Finally, MBR systems are a combination of biological treatment and membrane filtration. The final settling tank found in classic activated sludge systems is absent here. Instead, microfiltration or ultrafiltration membranes are used. This allows for very high-quality effluent and completely prevents the carryover of sludge in the water. MBRs are compact and take up little space, but their energy consumption is slightly higher. They are one of the most suitable technologies, especially for the reuse of gray water, stormwater, or industrial wastewater.
So, the common goal of treatment systems is the same, but the biological methods they use are different. Some mimic nature itself, some provide faster treatment by keeping microorganisms in suspension, and some maximize quality with membrane technology.
Absolutely. Each system has different advantages, disadvantages, and fields of application. Energy-efficient natural systems are more suitable for small settlements. Advanced biological treatment, or MBR systems, are preferred in large cities. The most important point is to choose the most appropriate technology based on the environmental conditions, population density, and water quality objectives of each region. Because wastewater treatment is not an engineering based on a single truth, it is a science where regional, ecological, and technological balances are considered together.
Yes, we have come to the end of our episode today. Today, we discussed the basic principles of wastewater treatment plants and the types of processes used. We also utilized the book Wastewater Engineering by Metcalf and Eddy while preparing this podcast. This was the first episode of our Wastewater Treatment Plant Design series. In future episodes, we will enter the plant itself. We will talk in detail about how units like screens, grit chambers, aeration basins, and settling tanks are designed and operated. Thank you for listening to us. Don't forget to follow our Instagram, YouTube, and Spotify accounts to be informed about new episodes. If you liked this episode, you can leave a like and share the topics you would like to hear in future episodes in the comments.